All right. So hello everybody. I'm Yang from Fixed Stars Corporation, Japan, and I'm happy to be given the opportunity to present at this fantastic event. And I typically want to thank Mr. Masayuki for inviting me to apply for the NuttX Japan meetup at the first place. Also, it was sadly canceled due to the pandemic, and I hope everybody is staying safe at home. So anyway, today I'm here to talk about a Linux compatible compound real-time operating system based on NuttX, Linux, and Jailhouse. So a bit information about myself. My name is Chong Fan Yang, and I know it's a bit difficult to pronounce, so please just call me Yang. I think many of you have contact with me have been confused that which is my first name, which is my family name. And I can say that Yang is my family name, and it's what people typically call me. So my hometown is in Taiwan, and I currently work in Tokyo, Japan as a software engineer at Fixed Stars Corporation. And we provide hardware and software-based optimization service to speed up softwares. So if you want to know more about what we provide, you can click on the link, or maybe you cannot click, but you can take a look at our homepage given at this link. So I have a hobby on tinkering with embedded systems and system softwares on my free time. So I think I can make quite some friends here. So this is about myself, and about the outline of this presentation. Today's outline is like this. I will give a presentation about what is a compound real-time operating system, and then into the implementation of the compound operating system, and also about how we handle system calls in this compound real-time operating system, which is the core of the implementation. Then I will talk about the performance of the operating system and give a short demo if I can. And finally, I will discuss about the issues and want to stir out some discussions. And I will also answer the questions. So first, before I start it, I must make some citations, or otherwise ACM will be coming after me. So this was developed during my years in graduate school at University of Tsukuba. I thank the university on supporting the development. It was proposed by me and my graduate school advisor Shinjo at this year's ACMVE conference in the title of Obtaining Hard Real-Time Performance and Rich Linux Features in a Compound Real-Time Operating System by a Partitioning Hypervisor. And because this presentation is limited by time, and for more detailed information, you can reference to this academic paper. Also, you might need to pay for the access. Or otherwise, you can reach me directly and I will try to give you a copy. So into the introduction, what actually is a compound real-time operating system? So basically, the idea is that we run two operating systems, a general purpose operating system and a real-time operating system together with a hypervisor on the same machine. And we do something to snap them together as one big operating system. And then we run process on this big operating system. And because this process is on top of the big operating system, you have access to both the benefits of these two operating systems, including the rich features of the general purpose operating system and the real-timeness of the real-time operating system. And the user benefits from this and can easily program real-time and has an easily programmable real-time environment. So an overview as a figure illustrated on the right, we have two operating systems, and we have given them two different names. First is the normal Lilim. It runs on Linux. And another is the real-time Lilim, which runs NuttX. And the hypervisor partitions the hardware resources between these two operating systems. The normal Lilim manages the non-real-time programs and devices. And on the other hand, the real-time Lilim manages those real-time applications and devices. It has a hard real-time IRQ path and has access to the Linux features via a shared memory. So how actually this benefits the community. So there's two different viewpoints. First is that it can be viewed as another real-time extension for Linux. It's comparing to other extensions, it achieves hard real-time, and on top of it, it doesn't require patching the Linux kernel, so it makes it very maintainable. Also, programmers can program with the POSIX or even Linux APIs, so it's very easy to use. And on the other hand, we can view it as a Linux extension for NuttX, which is a part of this implementation. It lets you execute almost any Linux program in NuttX without any recompiling or editing the binary. And also existing libraries, for example, glibc or other libraries can be reused, and also X-Window GUIs, which relies on the X-Window system, can be reused for this kind of system. So we propose the concept of a rich real-time process for this big OS that comprise of these two operating systems. It's written with standard POSIX API and threads, and it executes in NuttX, and it has a shadow process executed in Linux, and we'll talk about it in the next slide. It has a real-time and non-real-time threads illustrated here, and the real-time threads contains the real-time algorithms and doing real-time stuff, and interacts with NuttX kernel and the real-time devices via the NuttX kernel and drivers. And for example, you can access the timer, CANbox, SPI, all these like critical things. And on the other hand, there's the non-real-time threads, which access the Linux and the non-real-time devices on the Linux side, and also the rich features of the general purpose operating system, which is Linux, including the X-Window or TCP/IP stack via the shadow process, as illustrated in the green line here. And it's the key for accessing the rich features of the Linux in our design. So about this shadow process, it's like for each of the rich real-time process, there's a shadow process running in Linux, and it has a one-to-one thread mapping, and it executes the Linux system calls on behalf of the rich real-time process threads. And one important attribute of it is that the memory which it has, it shares the same physical memory with the rich real-time process, and in addition, it has the same memory address space. So the same data can be accessed at the same address in both processes. And this is very important attribute, which we will come back later. So about the implementation of this kind of operating system, first we talk about the hypervisor we used. Excuse me. So to create the two RAMs, the current implementation uses Jailhouse. It's a type 1 hypervisor like Zen, which utilizes Linux only as the bootloader and management interface, and it's a partitioning hypervisor, so the hardware resources are not shared, which means it doesn't do any scheduling on the virtual CPU, and the physical cores are assigned to the gates directly. And for the static memory allocations, it only has static memory allocations, but it might be shared between the gates. And finally, the devices are directly passed through to the gates, so the devices are not shared. So because none of the devices are shared, it can easily achieve the hard real time, and it's very feasible to run real-time operating system comparing to Zen or KVM or any other real-time, any other hypervisors. And because this is another presentation about Jailhouse, so if you want to know more, I suggest you to look at the Jailhouse's GitHub page given here. And for Linux running on top of a Jailhouse, there's nothing special about it. It's a typical Linux with a vanilla kernel, and only 2 kernel modules is used for shared memory address access. So next is about the real-time Linux, which runs our lovely NuttX. So it runs on top of the Jailhouse, and it executes Linux program binaries, which I say binaries means that it is not only the program which you compile it and run it on NuttX, which is the actual binary which will also run on Linux. So we exploit the fact that first, NuttX is process confirming, and so is Linux, well, mostly, which they have been broken many things lately. And on the source code level, portable programs should work out of the box if you recompile them. And if you have only a binary, then the system call set are very similar. The main barrier is the ABI of the system call. And also the virtual memory space, which in NuttX is very different from Linux. And finally is the non-standard system calls, which the Linux has screwed up. So if we provide the Linux compatibility layer, and somehow by magic, Linux program binary should work directly. And this is our development goal to make this compound real-time operating system happen. So first, it's like we ported NuttX to x86-64, and this becomes a byproduct of the development of compound real-time operating system. And it has already been merged back into the mainline recently, and I hope more people can help me to try it out and report bugs to me, as Intel chips behavior varies in a wide spectrum, from Atom to Xenon. Each might behave a bit differently, and we did have some reports of failed boot, and which I cannot reproduce, so I need more testers. So why x86 you might think, which is not so familiar with, not so common in embedded systems. That's because the Jailhouse only supports x86 and ARM64, and I just happen to have only an x86-64 machine for development, so I choose this. So in the entry x86 port was somehow between 32-bit protected mode and real mode before the 64-bit implementation is merged, and we extended into the 64-bit long mode and made it compatible to the system file ABI. And this work is mostly done by the compiler because the coding convention is like embedded into the compiler. But some about half of it is hand coded, including the system call handler, the context switch register set, and the FPU settings, etc. are all like referencing the Linux settings and properly set up for this build of NuttX. And so if you look at the x86-64 NuttX, which I have submitted into the mainline, you will see some historical things that relevant to the compound real-time operating systems. And you might think why this decision is chosen to during the port. And I can tell you the reason is like it is like taken out of the compound operating system and merged back. Okay, so then we make it compatible as a Jailhouse guest. And this become another byproduct of this compound real-time operating system, and it's also already merged back into the mainline. But it is not quite tested, and we really need more tester on this one, because I think the only person who has tested is sorry, I forgot about the name. It should be Brandon, I think. So I'm glad to help anyone who wish to test it to set out a Jailhouse environment. If you are interested, you can contact me. So the shared memory driver of this Jailhouse hypervisor is also ported, and it's not yet merged because first the PCI driver framework needs to go first before it can be merged, and then as the GPO issue, the driver needs a full rewrite, and I don't know how much is enough to call it a rewrite, and we can make it GPO free. So there is it. You have it, Jailhouse running NuttX and Linux side by side. So on the next step, we are going to handle the system calls in NuttX for these Linux binaries. And we create somehow called the Linux compatibility layer. So first, it's the memory address space issue. So we extended NuttX for Linux style process. And NuttX has some degree of protected in kernel build, which was for ARM and some other processors. However, they are quite different from the Linux address space environment. And I understand this is the path NuttX has chosen due to its usage in embedded environments. And it's nothing bad for it, but I'm trying to make it work with Linux programs, so I had to write some other things on top of it. So for simplicity, we extended a flat build, which is the simplest build of NuttX and to support linear style process. So first of all, virtual memory support is implemented for the x86-64 page table. And like Linux, kernel is mapped to the higher memory, and the process occupy the low memory, and for each process, the low memory will swap between the processes to create the different address space environments. And direct memory mapping is support is added for the MS system calls. And currently, there's no extra protection between the kernel and user space memory. So everything runs in 0, and we trust that whatever a user puts into NuttX, they know what they are doing. They are not putting something bad into the NuttX, into the real-time linear, into the NuttX side of the system. Okay, so next is about extending NuttX for the linear system calls. And this is the most important part. So it is really impractical to implement this going to be about 400 linear system calls in NuttX. However, the existing system calls of NuttX covers a good variety of this real-time usage. So what we need to do is we need a way to get overloads. First, nasty linear specified system calls which are not persist confirming, and then is the system calls which is inessential to the real-time execution. So we try to delegate those not important system calls to the side-by-side Linux. And because it's a true Linux kernel running side-by-side, so it gives an excellent coverage of the system calls. And it turns out to become a trade-off between doing hard or soft real-time when calling these dedicated system calls, right? So about the system call handler. To reuse we reuse the system call handler reservation mechanism, which makes the lower 512 system calls for linear system calls, and it effectively moves the NuttX system calls to over 512. So for this upper system calls, they continue to function as is as a typical NuttX system call, so native NuttX application will continue to function properly. And for those lower calls, they either been redirected to the NuttX calls, which in terms become a real-time system call, or otherwise, if the implementation is missing in NuttX, it will be delegated to the side-by-side Linux and become the remote system call. And this selection is seamless, this selection of delegation or not is seamless. That means that the user code uses the standard system call exception interface, and nothing else special is like into the code. So existing binaries should work out of box because they just call the syscall exception interface and seems to be done properly by the kernel. So for these real-time system calls, they are redirected and handled locally in NuttX using the NuttX implementations, and has a very deterministic execution and higher timing stability because we are running in a real-time context. And it gives access to the local facility, for example, the semaphore, the shared memories and accelerate, or like the timers, which is a device. And also to other real-time devices via the typical open read and write system calls, like paragraph of a Unix program. And on the other hand, there are the remote system calls, which provide access to the Linux features seamlessly. It gives access to the non-real-time devices which are hooked to the Linux kernel, and also the file system which are mounted on the Linux, or the credential which the Linux has, which is very complicated and difficult to re-implement in NuttX. And this delegation of system calls to Linux via queue. So for example, given in this figure, first, the real-time process, a rich real-time process triggers a system call, which go into the NuttX kernel, and the NuttX kernel finds out that it cannot handle it by itself, so it marshals the system call number and the arguments and send it via the queue to the linear side. And the linear side has a kernel module which will pick up the message and wake up the shadow process, which has shared the same memory with the rich real-time process. And the shadow process will call the system call on behalf of the real-time process. And the return value will be marshaled back again to the NuttX kernel and sent back to the real-time process. So the system call is completed. So what is difficult of implement this kind of remote system call is that the system call consists of pointer arguments, not only those typical value arguments, which are difficult to marshal because that it tells the kernel where to access the memory, and you don't want to copy the memory to the Linux because it's going to be very slow and difficult. So for handling these pointer arguments, that we make that important attribute that shadow process is made to share the same piece of memory and also the memory map, the memory address space environment with the corresponding real-time process in terms that the pointer has the same meaning on the normal reading part. So continue from this. Not only the system call is like multiplexed or selected between these implementations, the open system call is also handled especially enable access to files on both operating systems. It tries the NuttX file first, and if it fails to open, the remote system call will be called again to access the Linux files. And this effectively produces an overlap FS, placing NuttX file on top of Linux, and the returning file descriptor is like segregated to allow multiplexing on those system calls using file descriptors, including the read and write and select, pull, etc. So the lower part, the lower 4K are allocated for Linux files, and the top are allocated for NuttX files. And this effectively redirects the standard I/O input and output to the Linux side. So nonetheless, some of the system calls does not exist in NuttX cannot be dedicated because of the semantics problem or something else. And for example, it includes the process related system calls like the clone or fork, which you cannot delegate it because the process is running in NuttX. And also the memory management system calls like mmap and munmap because, well, the memory is also managed by NuttX. And finally, is the system 5 shared memory and IPC. Those system calls relies on the kernel facility, which you want to make it real time, you have to run it on NuttX. And finally, is these things that NuttX still considered obsolete and doesn't implement, for example, the alarm or those timer API which Linux has screwed up, like the timer FD. So we have to implement this using NuttX facilities. And we implement some of these system calls in NuttX, and it was some work and cost some time, but it's considered quite less to implement the whole set of Linux system calls in NuttX. And most of them are stuffs which just cause the corresponding NuttX implementations and do some decoding on the parameters, etc. It's not so difficult as comparing to implement everything from scratch. So right, next, finally, let's do system calls. And this is among those extended system calls that some of them have to be done both in NuttX and Linux to make the shadow process has a synchronous state of thread and memory with the real-time operating, the rich real-time process. And currently, the clone, fork, exists mmap and munmap and exec system calls are implemented as dual system calls, which like the both operating system will do something about this. So that's all about system calls. Now into the problem of how we start this kind of process. So in the current implementation, we implement the daemon in NuttX, and we use a loader program on the Linux side, which is very like in the typical LD.SL binary, which reads the EF binary, and it makes a remote access call to the daemon in NuttX side. Actually, it just marshals the binary path to the NuttX side. And the NuttX side process will create a seed-rich real-time process, which is like a case for the program going to start. And this rich real-time process will call the SF system call which in turn is a dual system call and dedicated to the Linux side, and we will start the user-appointed program in this shell. So into the performance of this real-time operating system. And I can think this is the first time like somebody used the same binary or same kind of program to like benchmark NuttX and Linux and compare them together. So the environment we use is a Xeon machine with this kind of with this software, which is NuttX 7.2 and Linux 4.9. And the configuration includes vanilla Linux and PRT patch Linux, and also this proposed compound real-time operating system with Linux, and also with PRT Linux. And finally is the infamous Xenomai 3.0, which is very popular in the Linux real-time community. So first we use the infamous cyclic test because, well, every real-time Linux test begins with a cyclic test. So a thread for cyclic test, if you are not familiar with it, it's basically a thread sets a timer and it waits for the timer to expire. And when it expires, it measures the specific time for accuracy of the OS timer facility. So for all configuration, we use the same binary, the Linux binary, except Xenomai, which it requires a modified version of cyclic test, which it has its own version. And the parameter given is in this slide. The test is performed on the 1 million second interval and do for 100,000 times. And during this test, we run a string benchmark in Linux as an extra load for the hardware and see how the system perform to this kind of situation. So the performance of the real-time rhythm, which runs NuttX, was the best, which best among all the solutions, including PRT with a 4 microsecond max latency and 4 microsecond of jitter, while Linux has somehow like 60 to 100 microseconds of maximum latency is shown in this chart. And the performance becomes better when we use PRT as the corresponding general purpose operating system in this kind of design. And this might contribute to that both sides have some real-time attributes, so the performance has become somehow better. And next, we to test the hardware input and output interrupt latency, and we measure the latency of the hardware interrupt. A serial device was attached to each configuration, and the system was programmed to generate output upon an input is received. So it's basically like you are waiting for IRQ on the GPIO, and upon receiving the IRQ, you output something else on another GPIO. And the reason we use a serial device because that we don't have a GPIO on the x86 machine. So the gap between these two pulses is measured with an oscilloscope, so you can know how long the system takes to respond to this pulse, this external pulse or external event coming in from external hardware. So again, the performance of this compound real-time operating system beats all other solutions, which has a maximum latency of 10 microseconds and 2 microseconds of jitter. And the performance also become better with PRT as expected. All right. So next is about the system call latency, and it's tested with the original system call micro benchmark from LLM bench. And the real-time system call are very fast. It's 4 times faster than the pre-NRT and over 4 times faster than the vanilla system calls. This contributes to that we ignore the ring switch and the protection of the kernel memory, and also attribute to the small footprint of NuttX, which doesn't do a bunch of things upon context switch. And on the other hand, the remote system calls are quite slow, up to 20 microseconds, which is expected because we have to marshal the information onto the queue and send interrupt to the Linux. And again, the thing had to happen again when the system call returns. But at least it works and it provides access to the Linux system calls. And to evaluate the effectiveness of this kind of dedication that we want to use system Linux side of features, we also run as window application in NuttX. And basically, what we've shown here is like what we have tested and have worked properly with expectations in NuttX, and while accessing some system code in NuttX, some in Linux. And I consider it's quite a success because we can run some quite popular applications, including like Xterm or GoScript or Imagemetric to show images using NuttX. So for now, I want to give a short, quick demo about this compound real-time operating system. Please let me start the sharing, and I want to switch to the console of my computer. So can everybody see my terminal, my console terminal?
Yes, I can show you your terminal.
Okay, so first now I have already booted the machine and run the Jailhouse. So first like I will rerun this script again, and I will show that currently that the Jailhouse runs 2 cells, which is another name given by Jailhouse to refer its guest. So you have 2 operating systems. First is the root cell, which runs Linux, and another is NuttX running on 3. And now on the NuttX side, I have prepared a short hello world program, which I can show you now, which is a hello world program which reads the proc version file and also print the contents of that file. So I will compile this one using the standard GCC. And then I will run it in Linux, which it runs and it prints out it's running on Linux. And can also show you that this is indeed a Linux binary, which uses the infamous LD.so binary loader linked with the GNU/Linux. And now, given a loader, which I have talked about, given this loader, I can load this hello world program into NuttX and will execute in NuttX, which now it prints that it's running on NuttX, and the file is NuttX. So the user actually doesn't feel anything when doing this kind of like running program in real-time rhythm or running on NuttX. So it basically feels like it's running on Linux. Everything is like Linux, but actually you are running things in NuttX, and NuttX are doing real-time stuff for you. And we can also, like, for example, I can get the license file. Oh, excuse me. I have to go to the correct spot, and can get the license file for you here, which is the license of this software I'm going to publish. And it's get it here, but also we can do it using NuttX, which I have changed this the path. I'm sorry about this. You can cat using the standard cat and the license, which also cats the license file. And we can find out that the cat is the system's cat, which in turn is a GNU cat, which works seamlessly in NuttX. And for more, we can also run, sorry about the long string of, all right, I am tired of this. Run a cyclic test, which will do a short test, which will tell us that the performance of NuttX side. And you also cannot feel anything different from running from Linux. And it's the most fabulous part of this creation. So here ends my demo, and I'll go back to my presentation. The presentation should be. All right, so finally into the issues and discussions. So first, the biggest issue of this kind of creation is the license issue. Currently, there's GPL v2 and the BSD license code is in the current source tree. And the first is the Jailhouse shared memory driver, which is ported from Linux, which is GPL v2, of course. And the rewrite is required, and I'm doing it, but I don't know how much is enough to make it happen. And then is the Linux code interface headers, or as known as the user space API headers. It contains the system code related structures and emulations, macros, definitions, and all those stuffs. And it's required to parse and translate the flags and structure into the NuttX form because NuttX has different definitions. So we have to do this for some of the system codes, even if it's real-time system code. And the GPL v2 is licensed with GPL version 2 with a user program exemption that user program can use it and it will not become a GPL v2 user program. But in this case, we are not a user program. We are actually a Linux kernel running side by side. We are actually operating system kernel running side by side. So maybe we have to rewrite it, but how much is enough? And will the rewrite save us, or even a rewrite will not save us from this awkward situation? Also, for the future works, contributions are very welcome to this work. And we really need more people to test this on more boards, because I have actually tested on only a single computer, because I only have that computer I can work on. And I need more people to test it. And also to test it on more Linux applications, because I have only tested on some of these micro benchmarks. And for those more heavy lifting applications with a lot of features, I need some real use cases that I can tell which this is working or not. And also, porting to ARM64 is very possible because Linux and Jailhouse is very available, and also NuttX is also available. So maybe this kind of paradigm of delegating system calls can be transported ported into ARM64, and more people can test it because ARM64 boards are more cheaply available. And one of the boards I am currently thinking of is Raspberry Pi 4, which Jailhouse has support in recent months. And I really hope someone can join us to do such development. And it's currently maintained out of the mainline, and I really want it to work its way back to in the mainline, because that it will strive to continue to exist even without somebody's support on some corporation support or my support on it. But first of all, we have to prove that such model is practical to in use and also beneficial for the NuttX community. That everyone is happy, then we can have it. And after all, the license issue had to be settled before merging, or otherwise some GPL code will be like going into NuttX, which is like anti-NuttX philosophy, in my point of view. So the current source code is hosted on GitHub page of my employer, Fixstars. And I would like to thank Fixstars for supporting my development on this project currently, after my graduation from the university. And I have been porting it back to the recent versions of NuttX and Linux. And the current port is for Linux 4.4, 5.4 and NuttX 9.1 and Jailhouse 0.12. And open tickets if you find any issues or you want to ask any questions. You can just open tickets on the GitHub repositories. So that's all about my presentation. Thank you for your attention. And if you have any questions, ask me in the YouTube stream. Or if you want to continue after this presentation, you can ask using this mail address or the NuttX online forum. Or you can open a ticket on the GitHub page, which I will also see. So any questions?
Great presentation. Congratulations, Changfan. We have a few questions here, and I have recorded them, and I'm going to ask you, all right?
All right. I think I can show. Then I can show the page because people may want to know my mail address or like some other stuff. Okay.
Okay.
Then you can start asking the questions. I'll be answering.
First of all, the first question is from Jonathan Gonzaga. He's asking, is it possible to implement this in a heterogeneous multicore processor?
So thank you for this question. And I think it's very possible. And I also have been thinking about it, but I don't have any available hardware for me to experiment. The only barricade for this implementation to work, or the only requirement for this to work, is a shared memory between the cores. So if you have a shared memory between the cores, then you can have the system call working. Because if you have a shared memory and you can map it at the same address, then you can dedicate a system call because the pointer argument has this correct meaning in the both the operating systems. And besides from it, I think this just implementation issue of porting Linux and porting NuttX to the given platform. And because you are using a heterogeneous platform, so you don't need the Jailhouse hypervisor, which I'm using, because it is already heterogeneous platform, provide two different rhythms for two different operating systems.
Great. The next question is from Gregory Nutt. He tells NuttX now supports OpenAMP. Could OpenAMP be used for system calls?
Okay, thank you, Greg. And yes, I have noticed that doing porting to 9.1 that in these 2 years since happens and OpenAMP is supported. And I think it's very possible that we migrate the cumbersome self-implemented remote system called marshalling and transferring mechanism via a shared memory queue onto OpenAMP if it's feasible for the semantics, and it will also be more easy to be maintained, and also the Linux has the support for it, so both sides will have a easy day. So I think it's very possible, but I will need to do some research on the feasibility of it. But I think the possibility is very high.
So the next question is from Philip Koval. He's asking a question maybe off topic, but what about NuttX on top of Linux kernel? Any use cases?
So thank you, Phillips. And what I heard is a bit like the simulation build of NuttX. Like you run NuttX as a user application on top of Linux. Or do you mean like running NuttX as a full operating system using a hypervisor, which based on Linux like KVM? I don't know which one you mean about. Maybe you can.
Maybe you can clarify it.
You can clarify it in the chat stream.
The chat, yes.
Yeah,
please,
I'm watching.
Philip Koval, where are you? Can you clarify it?
Well, maybe I can answer both the questions. First, if you run it as a simulation mode on top of Linux, then it becomes, well, actually, for both of the situation, the biggest problem is that if you run the scenes on top of Linux, then the real-time constraint is constrained by the Linux real-time constraint, because everything is like put it inside Linux, and Linux is scheduling the scenes. So if Linux cannot do things right, even NuttX do things right, things cannot be real-time. So that's the biggest drawback if you run NuttX on top of Linux using either the simulator mode or the KVM method. So the best part of using Jailhouse hypervisor is that it's running on another kernel, another core of the physical CPU, which the Linux has nothing to do with it.
Okay, I'm going to see if there is another questions here.
Yes, I do see.
We have from Andre. He's asking how difficult it is to access I/O from NuttX and Linux Interleavage.
Okay, so how I think of is like, for example, you have two UART. One is in NuttX, one is in Linux, and both are, well, becomes a TTY, a standard TTY, and presented itself in a div directory. And then you're going to use the open system call to open it and do you read and write and typical things. And I guess you can easily interleave it because you just open these two UART and use it. And the first, when you open the NuttX UART, you will first try the NuttX UART, and you will find that the UART is on NuttX and you will use it. And when you open the Linux UART, you will find that no, the UART is not on NuttX, and then you will try the remote system call, and you will get the file descriptor from Linux. And so for that file descriptor, you do rewrite, you will go to Linux. And for the former file descriptor, which you append from NuttX, you do rewrite, you will go to NuttX. It seamlessly dispatched to each kernel directly without any implementation, without any difficulty. So you can just interleave the calls and you can just program it, well, trivially. The only thing I can think of is that, for example, both TTY share the same name. Then you cannot open the Linux TTY because the file path is occupied by NuttX. So you have to find somewhere to change the Linux size file name or file path that you can access it from the NuttX side. I hope this answers your question. Any more questions? Or Sarah, are you there?
Sarah, can you hear?
I think we lost the host.
Yeah, but can you hear me, guys?
Yes, I can hear you.
Okay, so I think I found one here.
Yes.
What are the security implications? Does this open new attach surface from
Oh,
shape?
yes, I see this question. So this is an excellent question that, yes, it does open up new attack surface for applications. So in the current implementation, there are two attack interfaces. First, our Linux adjacent environment is implemented based on the flat build. So therefore, the kernel is not separated from the process. So the kernel stack, which is in the kernel, is accessible to every process running in NuttX. So first, I want to clarify that the Linux side has everything fine because we don't touch anything about Linux, but we touch NuttX, and the NuttX is running in flat build, so the attack surface are mostly in NuttX. So in the NuttX, first, every process running in NuttX cannot access others' address space, but others kernel threads, kernel stack. So that's the first security implications. And the next one is that in NuttX, for current implementations, we link the TCP of the NuttX and the Linux together. And somehow, if you tell NuttX kernel to transfer something bad, and the something bad go to the Linux kernel module, which handles the remote system calls, and it reads this and use that as the pointer to do the TCP, the process wake up and all those things, and the pointer is actually like bad, and then Linux will crash because there's a bad pointer for the Linux kernel. So most of the attack interface is in NuttX, and because of the Jailhouse is like jailing up the NuttX in a separate memory address space and kernel. So what I can think of is that, first of all, don't load anything bad into NuttX, then things will be mostly fine. I think, does it answer your question?
Yes, I
Okay,
think
yes.
you.
It has a follow-up well discussion.
Yeah.
Yes, it depends if the clarify the jailhouse isolation. I cannot answer this because I'm not developer of jailhouse, and the current space I trust it. But yes, it might break, and if it breaks, basing will happen. So of the base part is like this two can be fixed. It's just an implementation workaround currently in this implementation, and if you do it properly, then the attack surface will be smaller.
Okay. So I think we finish for now and for this presentation. And let's see if someone has some other question, please go to the forum. We have the link here in the video description, so you can go there and talk directly with Mr.
Yes.
Young.
Yeah, go there
Yeah.
and ask more questions. I will be very happy to answer them.
Okay, thank you very much for your great presentation, and also you create a new uh, NuttX architecture support. Thanks to this work now, NuttX supports the. Sorry, let me turn on my camera. Now NuttX supports uh, the Intel 64
Yes.
bits. Thanks to you and Brennan, great work.
Yeah, especially thanks Brandon because like he was doing some maintenance work after I pushed those code up onto the GitHub.
Yeah, and I hope we have some time later to let Brennan show NuttX running in the real desktop computer without
Oh, really?
emulation. Yeah, if we get the chance, maybe he try to do that, and I think it should be very great.
Well, be
Um,
appreciated.
I'm sure it was a very interesting solution, and I'm sure it will open doors for very interesting applications. And thank you very much.
Yeah, thank you too.
Now we will have a little break of 7 minutes. I don't know if Brennan can hear us. Brennan, are you up? Are you here?
Yes.
Okay. Can you please put the intro video to run in the background?
Yes.
Do you have it?
I might have the same sound system again. Can you put it in the chat?
Yeah, I will send the YouTube link in the chat. Okay. Just a second. Yes. Okay, Brennan, I just put it in the link. In this link, you will find the intro video. It's easy just to play it in YouTube and share your screen. So we can have 5 minutes of break now.
And only to remember all the participants, you can check the whole schedule at the NuttX.events.
Very good. Yeah. We have all the schedule with all the information about the speakers, about their presentations. So it's a good place to get more information about the next presentations. You, Sarah. Brennan, I think you forgot to share the computer audio because let me see. Yeah. Brennan, uh, Brennan, could you please put in full screen?